Welcome friends. So in our last video we have discussed a lot about the moment curvature relationship, deflection due to bending, yield criteria, and many more topics. So let us try to discuss a few things about the method of superposition. So it's so for this method of the superposition, it is a popular method for finding the slopes and deflections based on the principle of the superposition. If the response of a structure is linear, okay, so let's say here we have this particular structure. So this is 1 by rho, we can say, and mb in this direction. So if we have a slope like this, so then the effect of the several loads acting simultaneously can be obtained by superimposing, by adding the effects of the individual load. Okay, either you can say the method of superposition permits us to use the known displacements and slopes for the simple loads to obtain the deformations for more complicated loadings. So let's say, let me draw this structure here. If we can consider this small part for this at equal distance, let's say this is, here it is delta 1 by rho, and similarly more segments we can consider here. So at some equidistances, so we can say here it is again the same 1 by rho, and if this is our delta mb, similarly here this is our delta mb. Okay, so let the let the total bending moment be the sum of a number of contributions, okay, due to the separate loading. So for that we can suppose either if we have some slender member under several loads. Okay, so for that let us consider if this is our slender member and it is having several loads. So here it is the first load, here it is the load 2, here it is the load 3 or load 4. Several loads are applied on that cylindrical member, and like this, these are the supports. So for that this figure, this loads can be equivalent to the different, let's say here if we will draw some equivalent of this load. So here load 1 is at almost here. So this is our load 1 for this load 1, and that this is equivalent to this. Here we can say some another load means load 2 we have. So let's say it is here. So it is for load 2. So the bending moment due to this particular for third, fourth, so the sum of all will be equal to the total bending. So that we can understand, like if we will let me erase this, and so you can say total moment that may be mbb1 plus the moment due to the different loads. Okay, so let's let's say v1, v2, v3 and so on, these be the separate deflections. Okay, these are the deflections. Okay, so the total deflection is the sum of all the deflections due to the load 1, 2, 3, 4, and so on. So okay, so we can write as v as we have considered here the deflection, and so that is equals to, it's v1 plus v2 plus v3 and so on. Okay, so we know earlier in the last video we have discussed about the deflection, bending equation, and the curvature, moment curvature equation. So now let me write that particular equation. So that in our last video we have discussed this ei d square v by dx square. So that was our mb. Okay, so mb1, either mb2, or for different loads it may be different, so individually, and then we need to sum up all these moments. So this is b1, mb1 is the moment for the particular load 1, and for 2 it is different, so that we will represent by mb2. So here in that equation we have discussed that mb over ei, that is equals to del square v over del x square. Okay, so we can write here. So we we know if we will put the values from the equations. So for this we have a particular value of this m b and mb1, mb2, mb3. So for that we can say, so let's see here, let me write it, e I d square v by dx2 is equals e I. So that will be common for all these, and we can write it as d square over dx2, that is v1 plus v2 plus v3 and so on. Okay, so if we will distribute it, so it will be what it is, e I d2v1 over dx square plus ei again d2v2 over dx square and so on. Okay, so that is simply that this particular term can be represented by mb, and that is equals to, this is mb1 plus mb2 plus and so on. So this is nothing but the method of superposition. Okay, this is nothing but the method of superposition. Okay, so let us try to understand it with the case of a cantilever. Okay, so let me raise this first to have some space on this. So in the case of the cantilever, so if this is our cantilever, okay, like this. So if the length of this is L and a load is applied, if p is the load which is applied over there. So in the case of the cantilever, the bending due to the load p, okay, and the bending moment for this case will be like this, we can say it's m naught. Okay, so the resultant deflection, so the resultant deflection, if it is delta, so that is del 1 minus del 2. So if we will try to understand this, so this particular equation, this structure we can have in two different structures. So like here, let me this may be equals to for this, if we can have like this. So it is the p is applied. So what is our delta? So the bending occurs from this part. Okay, so this is what, this is our del 1, and this plus what, the bending due to, let me draw this here. So here it was So like this, so it is like this. So this is our value of del 2. Okay, and the moment will be mb along this direction. So so this is the resultant is what it is, basically the sum of these two. Okay, the deflection due to this and this value. So for an indeterminate system, okay, so let us draw some another figure. So for an indeterminate system, let's say it is a, and here it is fixed on this part. So let's say it's a c, and the load is applied here if it is p, and this point we can represent by b if l is the length of this beam. So the load is applied from a at a distance small a, and from b at a distance small b. Okay, so the what will be the bending if, let me draw some free body diagram. So for here it's a and c. Okay, a and c, so it will be the bending will be like this. Okay, so to understand it much more better way, in a better way, so we can understand by this, if this is our load p, so what will be the bending. So let's say it is like this. Here it is our del 1, and here it, if this curve goes like this, and if this is the horizontal, so we can have the angle phi 1 here. Okay, similarly for this we can say if this is the bending is like this. Okay, so for that, if here is some angle this phi 2, and this is our del 2, so what it is m note, so we can say this will be the bending moment, and this plus this and plus for the another we can say here. So if it is like bending due to this. Okay, so we can say it is the deflection is del 3, and similarly in this case also we can say it's phi 3. Okay, so what will be the bending moment? It can be represented by m c m b m a, like this. Okay, so from all the basic systems we can add all the systems. Okay, from all these basic systems we can add all the systems. So for that, if this can be, we can understand by, so it can be if del c, that is our final deflection, so that is our del 1 plus del 2 plus del 3. Okay, and if it is in equilibrium, so then in that condition it should be equals to 0. Okay, should be equals to 0, and we can say the angle may also be find out. So phi 1 minus phi 2 plus phi 3 is equals to 0. So basically rc and this moment mc uh, can be find. Okay, it can be find by solving in this fashion. Okay, so by solving in this fashion we can have the value of rc and mc also. So by using the values of basic systems. Okay, so then we can have the, I'm just putting the values directly here. So by using some basic systems, so from the table you can see, so the value of delta 1 is a square 3l minus a, okay, upon 6 ei, and del 2 that can be m naught l square upon 2 ei. Okay, for the free end, if del maximum we need to find out from the free end, from free end, so that will be, so the maximum deflection will be what, it is del 1 minus del 2. Okay, so we can put the values of del 1 and del 2 here. So finally you will get it's p a square and 3l minus a over 6 ei minus, let me write it here. So it is our, change this, so it's 3 m not l square, okay, like this. Okay, so hopefully you are getting about this, the method of superposition. Okay, thank you, thank for watching the video.